to this computer. Okay, all right. Let me expand this out so we can actually see it. Okay, so this is just like what I like to call like a quality of life thing, um, and just sort of makes me happy. And what makes me unhappy are unlabeled axes, right? So if we notice down here in this plot, um, I've got this flight cancellation ratio, which is just in a whole number down here, right? And I kind of have to go to the axis title to then see, okay, what does this actually mean? Um, that makes me a little depressed. It makes me kind of sad because it seems like it should be fairly trivial to just add like a percent at the end of this. Um, and in fact, it is. And there's a package that we can use called Scales. So install packages, Scales. I go ahead and get that installed. And Scales, as you might imagine, adds scales to my axes. So let's go ahead and load up Scales. Scales is something I use like constantly. Like I've got like three sort of like or four main libraries that I load on every session. One of them is Tidyverse, the other one Scales. Because when I go to plot something, um, I'm gonna want my axe because like I'm either using things in either dollars or percents. All right. Um, and so I want to be able to show that on my axes. You'll notice here that these are continuous, right? Meaning that there's no break. Like when I show this bar plot, like there's no discrete breaks here. Like it's a continuous bar plot, right? So the values, this cancellation, flight cancellation ratios value can take any number along the number line, basically, right? So, or in this case, anything from zero to infinity, right? There, you can have any value in between. So we call those a continuous, right? As opposed to, let's say, a discrete, right? So the values on the y-axis are discrete. They can only have specific values there. Um, One thing that I can do, what do I want to put this in here? Do the Y radar. And actually, let's go ahead and do some good coding practices in honor of Malia's good looking code. Um, I can do scale Y continuous. And I can do labels equals was it percent format, and I can add a scale. So you'll notice that I'm already doing like 0 to 100. I'm kind of multiplying by 100, right? So my percents are whole number percents, like 1%, 2%, 3%, 4%, right? As opposed to 0.01, 0.02, 0.03. So I can do a scale equals 1, meaning my percents are going to be whole numbers. And if I just do that and hit a plus sign at the end, if I hit Command Enter, pray to God that this works. It doesn't. Discrete value supplied to a continuous scale. Oh, not on Y, I'm on X. Here we go. There we go. Sorry, X. X is it. So see down here? I've got little percent signs now after my whatever. Right? That's kind of cool. Right? So you start from 0, 2.5, 5, 7.5. I can kind of get rid of this little percent notation right here. Yep. Let's run that, cancel ratio. Right? Does that look good? Do you like this or do you like or do you like this? We're back at the optometrist office. Option number one, option number two. I personally like option number two, right? It's unambiguous, right? Because you got to think for your audience, right? Your audience is not going to read the top. They're almost never going to read the title. They're almost never going to read your axes titles, they're always going to look at the pretty picture in the middle that you've drawn here. Like so, in this case, this gradient bar plot that we have, and they're almost always going to look at the data in there, right? And they're going to go, oh, so this thing ends at 7.5. And then they're going to go down below and read the title and go to cancel ratio. Oh, and I've got carry over here. So these must be cancel ratios. Cancel ratios for what? Cancel ratios for in-flight entertainment? Cancel ratios for cart service and during the flight? Like what am I looking at? And then I'm going to go to the title. Flight cancellation ratios for New York. That typically, like when people are um, looking visually at data, that's almost always the path they take. They always go inner to out. I don't think I've ever seen anybody, very rarely, like you're going to have someone go from the title to the axes to the labels to the interior chart. They're almost always going to go to the interior chart. They're going to say, what the hell am I looking at? And then they're going to go to then they're going to go outward, spread outward. And so it's always best to meet your audience kind of where they are. Um, and using this scales package and this scale X or Y continuous, depending on which axes you're working with. So in this case, we're doing the x-axis is our axes of particular interest. That's kind of where we want to be. What if so I had this like 100 times. What if I just got rid of that now? I could get rid of this scale feature in here and I could rerun it again. What does that do? Absolutely nothing. Why? Because it automatically, so by default, it assumes that it is going, oh, it's not going to do anything because I've got an error in my code. So let me back out of here. There we go. It by default assumes that you have percent data in your, that the data you want to convert to percent is automatically decimalized. So it's automatically in 0.01, 0.02, 0.03, so on and so forth. So yeah, that scales. Let me see, what other options do I have in here? Let's open the package real quick. I know that there is a bunch. Vignettes, help pages, blah, 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 blah. Scales, here we go. Scales, rescale, blah, blah, blah. Label wrap, there's a bunch of stuff in here. Bunch of stuff in here. Do I have, ooh, let me open up our scales package. I mistyped that package scales. Let's go to, there should be a vignette somewhere in here. Bug reports, Perl, skills are lib.org. Here we go. Here we go. Breaks and labels, breaks and labels. So you can do things like add particular suffixes or prefixes. You can add custom breaks in your data, and you can specify kind of how you want that stuff to show up on these axes. You can do dollar notation, right? Which is a big one. Um, Commas, right? Commas are a big one. So we've been dealing with data that spans orders of magnitude. So having a comma in there can be particularly nice. There's a bunch of advanced features if you want to get into like colors and stuff. Um, Give you some options there. You can do inverse axes. Let me make sure I'm not losing anybody here. All right, cool. You can do inverse axes, log scales, all different kinds of stuff, right? You can add custom suffixes and prefixes. So if you've got some sort of, custom notation, like, I don't know, children or whatever, right? We use basis points a lot, which is 1/100th of a percent. And so we will frequently review that with BPS. So I'll sometimes add that as a suffix. Yeah, scales makes life nice. Scales is really cool. It's one of those things that just sort of like you can tell you can tell who's good at R and who's not, who's really good at ggplot and who's not by the presence of these these little pieces of ornamentation in your chart, right? That I think is pretty cool. Yeah, that's one I want to go over. Yeah, we're still in week three. Let me think. What do I want to think of? What do I want to think of? Do I want to even do it or not? Neither of you have taken an intro stats class. Have you taken a stats class?
Not at Spelman, no.
No, Spellman. Neither of you. You took it in high school, I assume, right? Kind of, maybe a little bit. You don't know what a linear
Yeah.
regression is? Have you heard of the term linear regression? Do you know what it is? Maybe, kind of. Do you want to take a stab at it? Give me your best definition. Give me your best definition of a linear. I know you've seen it. If you just describe it to me, you'll probably get the definition right.
Manipulation of the question to
I'm
contract.
sorry.
When you creating of the question in a job,
You're just drawing a
the
regression on a
burden.
graph.
Yeah.
Yeah, kind of. Yeah. So, the easiest definition for linear regression is line of best fit. It's just line of best fit. That's all it is. So if I go to your data, Malia, and you see that negative kind of relationship on that scatter plot, um, if if I drew a line through that data such that I minimize the distance between all of those points, right, that would give me the line of best fit, and that would represent the relationship between, I think you had um, median income on your x-axis and poverty rate on your y-axis, right? And so that would exhibit some sort of a relationship. And the statistical significance of those variables represents um, how significant, right, that explanatory variable is for your outcome. So how much does your x-axis explain your y-axis? And you can in some way intuit it by the slope of that line, right? So if I've got a very flat line, then there's very little explanatory power in my x-axis variable. If I have a very kind of sharp line with very little distance between my points, then that will have very strong explanatory power. And linear regressions that will, in some sense, like, try to explain it. Is it a causal relationship? No, it's not. It's a statistical relationship, and there is a difference between the two, right? So, causal relationship is like, if I pick up this marker and I drop it, right? There's a causal relationship to the marker hitting the ground, right? And that's called gravity. Like gravity is a sort of causal relationship. That's not what we're doing here. What we're doing here is showing statistical relationships, right? So, is it the case that if I go to college, I'm going to end up rich later in life? No, not necessarily, right? Like everyone's paths are different. Maybe you picked the wrong degree, right? Like, maybe you got AI'd out of the economy, and you're one of the unfortunate folks that got caught up in the hype cycle. Um, maybe you chose a degree of passion that had very little professional relevance, right? Let's say you were getting a degree in art of some kind. That's kind of just a passion you wanted to follow, with little regard to professional success, compared to, let's say, economics, right? Economics, STEM fields, math heavy fields, right? To traditionally have a very strong relationship with future earnings. Um, and so, there isn't a causal relationship between the two, but there is a statistical relationship, right? Like in general, right? Like people who go to college typically do better off later in life than people who don't. And even if you pick, let's say, I don't want to say the wrong degree, but you pick a degree where, right, you're doing it more as like as a passion, um, just by being involved in an actual degree that you complete, just the completion of a degree, right, is a very strong indicator that you have the ability to like follow through on something, right? So regardless of what you get it in the most esoteric, obscure degree, right? In a way, it doesn't matter because you've followed through, you've graduated, you've shown you can complete something like that, and you've picked up skills along the way. Like, you didn't just take classes in your declared major. You took other degrees as well. You took an English class, you know how to write. You took some basic math classes, so you can, at the very least, like do some basic college level math. Um, uh, and so there, the relationship may be weaker, but there still is a relationship, and we can show those relationships with linear regressions. So the question then becomes, well, how on earth do I do linear regressions in R? And we're going to get into that right now. And so we're going to go back to our flights data. Let me see. All right. So going over my notes here, make sure we're on the same page. Let's see. All right. So good cancellation ratios. Is that right? All right. Let's look at, do I have flights loaded in here? I should. Flights. Yes, I do. So let's start with flights. So what do I want to plot? What do I want to plot? All right. So the question I want to ask right now is there a relationship between weather and flight delays? Right? Is there a relationship? Okay, that's kind of our question. Let me see if I can pull up a slide here. Here we go. Let me go up to here. Let me reshare this. Share my preview. Okay, here we go. All right. This away. It's up here so I can actually see it. You're not looking at that yet, are you? Let's go and share. Okay. So, like I said, regressions, right? It's a statistical tool. We're not necessarily looking, we typically want to do like causal relationships, right? But that's not really what a linear regression does. Linear regression looks at more statistical relationships. And it is the line of best fit, right? And so with linear regressions, right, we're trying to explore a question. So you've got a question in Emilia in your data that you can explore with this, right? So we kind of start with, what we like to think of as what we call a null hypothesis. And a null hypothesis is just simply, in the absence of any effect, right? What would we expect to see, right? And so for our question, our null hypothesis would be that weather has no effect on flight delays, right? And so what we want to explore then is whether weather is associated with flight delays, right? And the reason why we do this is because of around this question of what we call falsifiability, right? We want to be able to ask a question that we can falsify, right? And so we always start with the affirmative that there is no effect on flight delays, right? That there, so for your question, for instance, Malia, that there is no relationship between median and household income and poverty rates, right? That would be your null hypothesis. And so when you run your regression, really what you're testing for is there a relationship, right? And if there is a relationship, I should get a parameter that has a very high level of what we call statistical significance, right? And we sort of arbitrarily define those as in terms of confidence intervals. So you've heard of the term like the 90th percentile, the 95th confidence interval. Um, what those are representing is how much could we attribute to random chance the data we see, right? And so what a 90% confidence interval says that there is a 1 in 10 chance that this is just purely random. Like I get this result just because of just a random draw, right? A 95% interval says a 1 in 20 chance or a 5% chance, right? 99% confidence interval says there's a 1 in 100 chance, right? How do I choose those? largely just you just pick one. It's sort of defined upon the question you're asking, right? Like if I'm looking at flight delays, right? Maybe 95% confidence interval is the appropriate interval. Why? Your flight gets delayed, big deal, no big whoop, right? If I'm looking at let's say vaccine research or cancer research, do I want a higher or a lower confidence interval?
Higher.
Yeah, higher, right? Especially something like where someone's life is on the line, right? Like if I'm looking at medical research, right? I'm not happy. Like if I remember I was sitting in a doctor's office with my wife and um she, we were looking at some stuff, like the doctor was showing us some research because of course, like I asked for the research. Like I'm that guy, right? So I asked for the research and he's like, oh yeah, so 95%. I'm like, what's that? 95% confidence. I'm like, hey babe, that's 1 in 20. She goes, oh dear God, that's horrible. Like 1 in 20. Like 1 in 20, you can see, like you can almost touch 1 in 20. 1 in 100, it's getting thin, right? 1 in 1,000, all right, that's rare, right? Like I can't really think like 1 in 1,000 is like, that's those are strangers, right? 1 in 20, that's like a friend group. 1 in 10, that's like my family, right? That's kind of way you can think about it. Like if the effect is on the order of magnitude of like a family, like this is like, you know, uh those are like popular trends and whatever, right? Like you're just looking for a weak significance, like some sort of effect. 1 in 20. Okay, getting a little bit more serious here. Like I want to be a little more certain. 1 in 100, 1 in 1,000. Those are, we reserve those for effects that have major significance. So let's go ahead and so we're going to take a look at flights and weather data. Let's go ahead and combine those into a thing called regression data. Do some group eyes and summarize, compute the average departure delay by month. Make sure we deal with any potential NA values, of course. And then we're going to do some GM calls to create some bar plots, kind of like what we did with the cancellation rate. We're not going to do that as a breakout because it's just like the three of us this morning, so we can just all do it together. That's fine. And I kind of want to walk you through exactly what we're thinking of here. So let me share up my sesh. Safari class notes, share. All right. So linear regressions. Question. Is there a relationship between weather and flight delays? Question mark. All right. So what do I need? Well, first thing I need is flights, which I have flights. I don't have weather, so I need to bring that in. If you don't have flights already loaded, we may need to get that loaded in here. Let me see what packages I have loaded. I have AR. Do I have flights NYC loaded? Let me just go down here. I have that loaded. Okay, so I've got that package loaded already in here. So I can just go data. Should go, we'll take weather. That should just load fine for me. It does. Let's examine weather. Anytime now. There we go. All right, here we go. So in weather, I've got origin, right? Year, month, day, hour. Okay, that's cool. And then I've got some other uh, features that are particularly interesting. So we've got wind gust, wind speed, wind direction, humidity, and then precipitation. So you'll see in here, these are precipitation levels. Let's go and put up weather real quick. So weather has, day, month, year, hour, humidities, dew point, wind direction, speed. Okay. Precipitation in inches, right? So this is the amount of precipitation collected by, oh, there we go. Yep. So I got some precipitation values in here, right? So I got some, in inches. So what would you expect to see? So without plotting anything, right? What would we expect to see between flight delays and rain? What kind of relationship would we expect to see?
An increasing relationship.
Yeah, it's supposed to see kind of a positive relationship, right? Like, can planes fly in the rain? Yes, planes can fly in the rain, right? Like, we know that. But what we expect to see is that when this precipitation figure gets pretty high, that means we have a particularly strong storm, right? So we would expect to see, higher cancellations as this number kind of ticks up a little bit. So we're kind of using precipitation in a way as a proxy for storm severity, right?
Sorry, mine says data set flights not found and weather is not found.
Oh no. Go ahead and type. Let's go. I'm gonna comment up it. NYC flights 13, and then library. So you may need to install that package and then run that library, and then we'll do data flights. And that should get you flights, and then this next one should get you weather. So I had mine automatically loaded, but you may not have that loaded in your in your environment. Let me know when that is done running.
Okay, right now it said restoring our session, so it's restalling everything.
That's fine. Let me see. I will continue along, and I've got this shared up too. So if you fall behind a little bit, following along, you can just kind of dive in here and grab the code. Um, so what I want is, um, I want data that has both flights and weather. And so let's see. Go back in here. So this is weather. So I've got, again, God bless. Restore project. Here we go. All right. Where am I? So weather has year, month, day, hour, and then I've got this particular time hour factor in here. And so what I want to do is I want to match, right, the specific time that a flight was taking off with when yeah, this the specific time of this weather, right? So those two together should give me some sort of indication of um, uh, you know, what weather was happening at the time that that flight was scheduled to depart. Let me go to flights. Yep, there we go. So I got year, month, day, and then I've got travel time, tail number, destination. I've got hour, and I've got minutes. So you would say hour. Don't have minutes, but I do have time hour. So time hour is going to get me pretty close to what we want. So it's gonna get me, I guess, sort of within um the hour, right? Is kind of the nearest bit of resolution. I have a minute in here by chance. I do not. So time hour. So the closest weather resolution we can get is within the hour, if that makes sense. So I've got flight data down to the minute, but I've got weather data down the hour. So let's go merge these two together. I want to merge these two together. So I'm going to start with let's do regression df. Do regression data equals flights. And then I want to do an inner join. So what an inner join is going to do is remember your joins. So it's going to return only those values where I have both um, data for the weather and data for flights. So let's go ahead and bring weather in, inner join, and I've already got X because that's flight. So now I want to bring in weather. Now, what do I want to join by? What do I want to join by? Well, I want to try and make this as clear as possible. I want to make sure I'm matching one for one. And so I obviously want year. I want, bring my little notes down here. I want to bring in year. I want to bring in month. I want to bring in day, right? I also want to bring in hour. And I also want to bring in time hour. Because that's going to give me sort of like my complete observation. But I don't want it for everything. I want it specifically for my origin airport, right? I want it for my origin airport. And if you recall, what's in origin airport flights? Let's go to, yeah, I'm just going to go down the console here. Let's see. Whole origin. And then I'm going to use the function called unique. That's just going to give me all the unique values in that. Okay, so I've got my 3 origin airports, right? EWR is Newark, LaGuardia, and JFK. So, I forgot to put in by. Join by. All right. So what this is going to do is it's going to take flights. I'm going to interjoin it with weather. And I want it to join by year, month, day, hour, time hour, and origin. And so that's what we're going to do. So if I do that, I should get some regression data. And I do. I do get regression data. I get a lot of regression data. I get 335,220 rows of data. If I go up to my flights, did I lose anything? A little bit, lost a little bit, right? Right. What do you say? So I started off with 336,000. I now have 335,000. What do you suspect we lost in between those two? If you guys remember from like last week. I know it was like a week ago. Give you a hint. Probably cancel flights. These are probably going to be our cancel flights that we lost, right? So these are flights that actually departed, right? So we're losing those cancels. Those are, if you remember those NAs that we had in our data set, those are automatically, for the most part, being chopped off here. So we're losing those NAs. Let's go back to here. So what I want to do now is calculate, go back to my notes, compute the average departure delay by month, right? So let's go to flights. So this is our regression data. So this is our regression data. So now average delay by month. All right. So we know that this is already 2013. So I have to think about the year. So all I got to do is think about what's in this. Let me get rid of Chicago flights, weather, get rid of CA schools. So all I got to worry about is what's in this month category. So I'm going to start with flights, right? And I'm going to group by what? What am I going to group by? Anybody? I saw you say something, Malia. I saw you say the right answer. Huh?
I don't know if it was right, but I said group by flight.
Now group by flights. We're going to group by. So if I want to do the average delay by month, I'm going to group by what?
By month?
Month. Good. Awesome. Month. We're on it. You guys are great. I love it. It's so hard doing online stuff, by the way, like getting like it's 8 a.m. Well, now it's 9 a.m. You've been hearing me talk for an hour straight. But like, yeah. Well, this is like West Coast. This is what, like 6 a.m. for you? Dude, both you guys are just absolute just machines. Anyhow, yeah, this is always tough doing this kind of stuff, but I appreciate you guys staying alive with me. So I want the average delay by month. Um, do I want to mutate or do I want to summarize? Do I want to change my data or do I want to summarize my data?
Mutate?
Not really. So if I mutate,
Oh,
I'm gonna change. Yeah, I'm gonna summarize. So I don't want like an average for each one of these 335,000 rows because that's just I mean I could, but that's not cool. What I really want is just a summary, right? I want to take all the data by month and I want just the average in there. So we're gonna do a summarize. Um, let's do average depth delay equals mean depth delay. If you remember, like there's some NAs in there, right? So um, I can either drop all those observations entirely, or I can just tell my mean function here to ignore them. I'm going to use my mean function to ignore them. So na.rm equals true. And I got to close that out. And then now I want to see what we got. So I'm going to pipe that into a ggplot. I'm going to do geom call. And then ABS, X equals, what is this? X equals month, Y equals depth. Nope. Average depth delay plus theme minimal. Yep. Because I like my stuff nice and clean. Labs, X equals month. Yeets. Y equals average departure delay. And I'm going to just put here minutes so we know. And if I run that, I should get a plot, bar plot. X-axis is the month, y-axis is the departure delay. And if I hit that, it's exactly what I get. So if you run your stuff, that's what you should get. And for right now, we're going to ignore this stuff here. Actually, let's do this. Scale X. Let's do this. Let's make this even more interesting. Let's do. There we go. That's nice. Is that weird? Do you see these half marks? What's month 2.5? I don't know what a month 2.5 is. Like between February and March. It's not a real month, right? No. We grouping this by month. So what we can do is we can just throw factor month in here, right? And that'll automatically do factor levels on our months. Which when I do that, oh come on, dude. You're on it. Plots this. That looks better, right? Right. So now I got months down below, and I've got my average departure delay in minutes along here. Okay. Um, do we think that this is different by airport? You think that might be a factor? You think maybe one airport's got their act together more than the other? Maybe. Yeah, could be. Maybe. I don't know. 335,000 rows of data. It's a lot. It's a lot of data to be hunching on. Let's go look. Let's find out. So let's go ahead and just copy and paste our data. And I'm going to say average departure delay by month and airport. So if I'm going to group by month, I'm going to group by month and what else? Yeah, I think I see. I can read lips really well. I think you said origin, Malia. I think you said origin. All right, I'm gonna do origin. All right. So we get summarized average departure delay. That's right. So what this will do is this will go through and this will uh, calculate the average departure delay for each airport for each month. My code's getting messy now. I want to do my fill equals origin, right? So if you remember, um, uh, I want this. I don't want gray bars, right? I want the fill to be related to the airport. But then now I've got to deal with the position. So let's just run this, see what happens. Let's just see what this does. All right. So I get this. Is this informative? Kinda, not really. Right? Why stack them? Like, is there like I shouldn't be stack like they kind of say the same thing, but if you notice, like this is now 60, this is now 20. They're not like these average, you don't add averages together, do you? Like that's not something we do. So I want these to be separate. Like I want these to be next to each other. So to do that, I use the position flag equals position underscore dodge. Right? Is that right? Yep. Position underscore dodge. And what dodge will do is it'll kind of like dodgeball, right? It'll cause these to show up as their own separate bar. So I run that. Huzzah. Huzzah. All right. So I have average departure delay in minutes. I've got the month, and the colors correspond to the airports. And so I guess the question for you guys is, you know, what do we like? What do we notice in this data? Do they all kind of say the same thing for the most part, or does someone kind of pop out at you?
JFK pops out.
JFK pops out a little bit. Yep. JFK kind of peaks here in July, right? Um, they all kind of follow the same trends, so more or less, right? They kind of, you know, sort of do the same thing. But what's going on in New Jersey, bro? Like, it looks like New Jersey is a bit of an outlier here, right? They kind of have a pretty like they kind of peak here in well, I guess what is this the spring, right? And then they go through a second peak with everybody else, and they really peak here in December. And so one has to wonder why. Is that related to weather or not? I don't know. I don't know if it's related to weather. It could be other factors, right? It could be um there could be like a migration effect going on in December, right? Folks flying home for Christmas, right? And for whatever reason, Newark is the airport you do it from. Think about college kids, right? What happens in December? Finals are done. We go home, right? So are there any big schools in New Jersey? Yeah, there's a ton of big schools in New Jersey. Maybe it's cheaper to fly out of Newark than it is JFK and LaGuardia. And those could be factors. But in general, I mean, they kind of do follow the same trend, right? We see this sort of increasing trend through the spring and into the summer, and then in the fall, we see this decreasing trend, and then we see it increase again, sort of in the winter, right? So there's a seasonal effect here that we would expect to see, right? When do we see some winter storms? We see some spring storms. We see some summer storms. They seem to happen right around when we expect to see them. Although Newark does sort of have this much higher average departure delay. Um, and that, I think is sort of a question for further exploration. You guys can do on your own if you are so interested. I am not for right now. The question is now, though, precipitation and flight delays, right? So is there a relationship between precipitation and flight delays? How might I want to show that? So let's do average depart departure delays, and precipitation. Right. So we've got this data that we created up here, this regression data, right, which brought in over um, both our flight data as well as the weather data. If I just inspect this briefly, year, month, departure time, right? Departure, we got departure delay in here, arrival time, scheduled arrival time. If I keep going over, I should hit weather. I got temp, dew point, humidity, wind direction, wind speed, wind gust, precipitation, pressure, visibility, right? So I now have a data set that has both my departure data or my flight data as well as my weather data. So let's go ahead and start with that. Let's go on our regression data. Oh, and let's go ahead and do a group by precipitation. Yep. And I want to do a summarize average depth delay equals mean depth delay. NA to R equals true. Let's go ahead and make sure you're treating those NAs appropriately. Let's go ahead and just plot this into ggplot and geom. Let's do a whenever we're doing the relation between two variables, right? We almost always want to use a scatter plot, right? Because that's going to show us visually if there is a relationship. So we're going to do a geom point ES, and I want to do x equals precip, y equals average depth. I don't like the underscore here. This bothers me. Get rid of that. Depth. Delay. And I'm going to do a theme minimal. And I'm going to do a labs. So x equals precip inches. Y equals average departure delay in minutes. Okay, so what did we do here? We start with our regression data. And so what I want to know is there a relationship between precipitation and average departure delay? In theory, I could sort of plot all that data out, like kind of in a scattered way. Um, but I may want to average that. Why are we grouping by precipitation and then doing an average? Well, because we know that we're looking to we're using this precipitation as sort of our like as our proxy for weather. And so it's not the case that I'm looking for a one-to-one relation between precipitation and average partial delay. I'm just looking to see on average, right? Does precipitation have an effect, right? And so by grouping by those levels of precipitation and then taking an average of the delay, it helps kind of smooth over a lot of those. I would expect to see a lot of variability in some of these data points. And so really what I want to do is just average over some of that to help kind of trim out that noise. How much, what do my ranges of precipitation have? Let's see. Let me see. Let's do weather. I'm going to do poll. Precip. And I'm going to do range. And what range is going to do is going to give me the min and max of my data set. And if I do that, what do I get? So the ranges go from 0 to an inch, just under an inch and a quarter. So let's see now, what does our, what what range of precipitation is in the data? Okay, let's go to spots. We are grouping by precipitation to average out the noise to get a cleaner signal. All right, so what do I see here if I do that? Beam mole. Right, so if I do that, right, so what do I get? I've kind of collapsed my data. I've taken this like 335,000 rows, right? And I've kind of collapsed it down by looking at the precipitation in inches. And so on average, right, if I get a quarter inch of rain, right, I see anywhere between, call it a half hour to, what is this? Between a half to 30 minutes to an hour delay, right? All right. So when we see, quarter inch of rain an hour, right? We're looking at about a half hour to an hour delay, right? So when I go up to like an inch an hour, right? These things kind of start blowing out here, don't they? Right? These are fairly extreme values for rainfall, right? Like an inch an hour is like that's like hurricane level kind of stuff. Um, and so in general though, right? Like the more rain we get, the higher the delay, right? Because if you think about, flight operations, right? Can airplanes fly in the rain? Yeah, sure. But like, can planes necessarily march their way down a runway when there's like a half inch of water? Like, I mean, that probably not, right? That's probably not like safe, right? And especially if you think about like if, God forbid that like, you ever have to abort a takeoff, right? And you're in one of these situations, it creates a bit of a challenge. And plus, if you're getting this much rainfall in a short period of time, chances are you're also experiencing significant wind. You're also experiencing lightning and other things that are probably not that safe to fly in. Okay, so we know that there's a relationship between, this rainfall and the average departure delay. Um, so now I want to do something with this, right? I want to find what is the line of best fit through this data, right? So my line of best fit through this data, right? So regression equals line of best fit, right? So if you guys remember back to your algebra classes, right? So y equals mx plus b, right? And so b is our intercept, x is our data, right? So this would be like our precipitation in inches, and m is our slope, right? And m is how much of an effect does x have, basically, is our interpretation, right? So the bigger the m, the bigger the effect x has on our y, is the best way to explain it, right? So if you think about like y equals, let's say 3x, if I put x equals 1, y equals 3, right? If my m equals a half, I put in 1, y equals 1/2, right? So there's this kind of positive, nice linear relationship in our data. We like linear effects. They make life nice. Um, how do we do this? Even think about doing this in R. All right, you're in luck. And it actually even does it in ggplot for you, which is even better. That's even the better thing. I'm gonna show you. So let's go just copy our stuff over because we are efficient students. I've got my average departure delay. I can use a function called geom smooth. And what geom smooth does is geom smooth will plot out the line of best fit through our data. And we have a bunch of different functions we can use. And what I want to show is method equals LM. LM is R's function for linear model. It's called, literally it stands for linear model or linear regression. So it's going to plot a line of best fit. And so automatically in R, what's going to happen is it's going to fill this in for us, right? So I've already set Y, right? My Y equals average departure delay. I've already set X. X is precipitation. And so what's going to do is it's going to use this linear model to then estimate an intercept and the slope. That's going to do it for us. If I do that, I get an error. What happened? Jam smooth problem while computing stat. Error occurs second layer requires a flying missile. I have an aesthetic, bro. Okay, so I don't have an aesthetic. Let's do AES. X equals percip. Y equals average depth delay. No, the math equals zero. See what that does. There we go. Now I get a line of best fit. I forgot. I'm not declaring my aesthetics globally in my ggplot up here. So I think, Malia, you've done that in your plots before, which is okay. I like to declare mine individually. That's just a personal preference for mine. But when you are doing things like additional geometries, you may need to declare the aesthetics again inside of here. So, which is what we did. So you caught me in the middle of an error. So we get a line of best fit. So this line of best fit, what this represents is the straight line through the data that minimizes the distance between all of these points. And so literally what is happening here is in the linear model, it is calculating the distance between all of these points. It's square summing them, and it is then finding the line that minimizes that sum squared difference. You'll also notice that there's a shaded region around it, right? And the shaded region around it represents the standard error, right? So this is kind of how confident our linear model is at this particular point on the line. And so you'll notice that it kind of starts off, it kind of narrows out a little bit, kind of does a little hourglass thing, kind of narrows out in the middle here, and it really widens out towards the end, right? And so if I look at my data points, right, can I venture a guess maybe why? What do I notice about these points around here? They're kind of close to the line, aren't they? All right. They're a little bit farther away here, right? They're kind of close here, and they kind of blow out towards the end here, right? And so that's what the standard error is really kind of representing, right? Sort of representing the distribution of the data that you're trying to fit, right? And so you may think of these points as being maybe like outliers, right? Extreme outliers. It's there's just less data out here, right? There's not as much data. There's a lot more data over here, so it's a lot narrower. There's less data out here, so this error band is a bit wider, and that's really kind of what it represents. Let's see now. What about we noticed with the airport? Right? So we noticed that airport appeared to have kind of a particular effect. How do I want to add in the airport factor now? Like, let's go and say, okay, this fits. Say notes. This is for all airports. All 3 airports. I got 5 minutes left to do this. One thing I forgot to mention. Where does the line? What's the intercept on this? Where does it cross the y-axis? Does it cross at 0 or something other than 0? Kind of crosses it, something above 0, right? So, what this represents is that in the absence of any weather, I can expect to experience a roughly 30-minute delay, right? So on average, if I'm going to get a delay, it's going to be about 30 minutes. Is what this is telling me. And then once we add in precipitation, I then increase the degree of the delay. Is really what that's telling me. So I got a bunch of zeros here where I still had delays. Does this mean that weather doesn't have an effect? No, I'm only looking at precipitation, right? What other kinds of weather could I have? I could have fog. I could have wind. Um, what else do I have in here? Heat, right? Perhaps heat is another one. So if I know it's going to take 15 minutes or 20 minutes to march a plane down a runway, and it's not until we get in the air that an AC in the plane really kicks on. Do I want to leave my passengers in 100-degree heat in the middle of July on the air on the tarmac? Probably not. Those are going to be miserable passengers. So they may leave the airplane at the gate until they can get them down the runway in a decent fashion, and that's going to add to the delay. Um, so that's kind of what our intercept looks like. What if we break it down by 3 airports? What if we break this down by each airport? It's going to take our data again because we're efficient. I'm going to copy it. I'm going to just paste it down. And I'm going to do group by precipitation and origin, kind of like what we did earlier. Get my average delay. I got my stuff in here, right? Points. Yep. All right. So if I do that, I need to add, I need to add some color in here. Color equals origin. Right, so I need to add a color equals origin, and I want to do the same thing here. Color equals origin. And if I do that, I should get something that looks like this, is what you should have. You should have something that looks like this. Yep, should have something that looks like that. So what do we notice? What I notice is that there's a pretty strong relationship at LaGuardia between they all have roughly the same intercept, don't they? Right, they all have roughly the same intercept. And if we go back to here, let's see. So it looks like there's a much stronger relationship with the weather at LaGuardia than at either JFK or Newark, which is interesting. It's not something I expected. Like there's some pretty monster delays here in LaGuardia. So these blue points in LaGuardia, I got some pretty monster delays. If we go back to this plot here, right? I kind of almost expected, right? Like maybe Newark would show something interesting, right? Maybe Newark would stand out to me. That if I just looked at this bar plot, like if you just asked me like which one of these are the same and which one doesn't belong, and I would have told you look or Newark does not belong, right? But I go over to here and I get the exact opposite answer. In fact, LaGuardia is the one that kind of stands out, and JFK and Newark look a lot closer to each other, don't they? Right. And so that's kind of that's kind of the magic of doing these types of regressions, is that you're able to suss out data in a much more deliberate way, a much more statistical way than just using our eyes lie to us. Our eyes deceive us. Shakespeare was right. My eyes doth deceive me. Right. Um, and this is how people lie with data. If you want to, when I told you, like, what I want you to take away from this class: one, know how to do some art. Just be productive. Just know how to play with data. Two, how do people lie with data? This is how people lie with data. They'll show you this and say, bro, Newark is the pits. Newark is horrible. Go to JFK. JFK is so much better. Well, okay, I did. And guess what? I'm no better off. I'm no better off with regards to precipitation than these two features. Well, what else are we missing in here? Right? I'm missing wind, I'm missing temperature, I'm missing a bunch of other features, right, in the data set. it's worth exploring. These are all different interaction terms. But at least at first glance, right, I can see like, actually, no, like the second it rains at LaGuardia, my delay times go through the roof, right? That's kind of what this says, at least in 2013, right? And so why is it that that LaGuardia is so much more affected by rain than everyone else? Like they're in the same geographic region. Like it's not like they're like in different parts of the country, right? They're like literally across a river from each other. Um, I guess maybe alternatively, like what do we notice about the slope of this line? Pretty flat, isn't it? It's pretty flat. So like why isn't precipitation having an effect? What's going on with ground operations between Newark and JFK, right? That's causing these delays. If it's not weather, then what is it, right? So it could be the case that, LaGuardia is really the airport you want to go to, right? So, they're the ones that are not experiencing these kinds of delays as often as these other two airports. And so that may be something worth exploring. So this is kind of your signal that like if you're just looking at these bar plots, is that enough? Probably not. There's other factors we can go through. And we can do it by precipitation, we can do it by wind, you can do it by all different kinds of factors. But the big thing is that we can use a simple function called geom smooth. Geom smooth did the work for us. Kind of did the work for us, right? Does it tell us our statistical significance? No, it doesn't. That we can go into that perhaps on Monday. Actually, we will on Monday. But if you just want to get a line of best fit through the data, just to kind of see the overall trend, we can use this geom smooth function to go and get there, do the heavy lifting for us. That's all I got. So homework over the weekend. If you guys could give me some data, give me some plots, I'll send off project update 2, and you should be able to start getting that filled in. So on Monday, we'll start off with show me your screen and show me kind of what you're working on, and we can get through it. If you guys need office hours because you're running into issues with stuff, reach out to me. I'll be around tomorrow. We've got a couple of office hours already lined up during the day. So if you want to add to the calendar, I'm more than happy to get you guys in. Or if you want to punt to next week, we can do that as well. Because we only got a couple days left. We got like 4 classes left. And you guys are already doing linear regressions. That's pretty awesome. That's incredible. All right. I'm gonna leave you guys be. Enjoy your weekends. Enjoy your Juneteenth. And hopefully the weather is going to be in your favor. Doesn't look like it for Atlanta. Looks like it's gonna be pretty rainy. So hopefully you guys have a little bit better time. And I will see you guys on Monday.
Thank you.
Awesome. All right.